Okay, let's go ahead and get started. I'm super excited that we're actually here and celebrating, the 30th annual CSM workshop, and also getting the opportunity to recognize Warren Washington's amazing contributions to Earth system science. We've been thinking about this, Elizabeth and I and others, for at least the last year, so it's pretty fun that it's actually coming to fruition. I think we have a pretty fun afternoon and evening schedule for everybody. 30 years, it's really remarkable, right? That a project can sustain for that long in general. And if you think about all the remarkable things we've accomplished with CSM over the years, and all the people and faces and that we've got to experience during that time. And it's really fun for everyone to, every year we come back to this workshop and you meet all your old friends, and then you meet all the new young people who are coming and with all their new ideas. And so I feel really honored and really humbled actually to be up here and leading this event in honor of CSM. And so I'm going to do a fairly predictable thing, but I think it's still going to be fun, which is to try to see how many workshops people have been to over the years, because we do have some people have been around for quite a few of these. We'll see. So I've been around. This is my 22nd workshop, so I'm no spring chicken myself, but I'm not the winner. That's obvious in terms of the longevity. But I'd also start up by let's recognize, and if everybody's ready to do a quick stand up, I want to recognize all the people who this is their first CSM workshop, and it's really fun that you get to be here for this event. So everyone, please stand up who's your first workshop. All right, so 30 years from now, we expect you to be celebrating the 60th. So then let's go for people who've been to, up to 10 workshops. Can you please stand up? If you can remember, and just go approximate. We don't need to go. Yay. You guys, you're trying hard. You're trying hard. That's good. Solid effort. Next, let's do 10 to 20. 10 to 20. All right, some former chief scientists. Okay, let's do the 20 to 25. We're going to get a little bit more fine-tuned here. All right, I do recognize all those faces. Okay, 25 to 29. All right. That's dedication. And then finally, let's see who's been here to all 30. Please stand up. Yay! We got Esther in the back there. Steve, are you standing up? No, Steve is not standing up. Jerry, Peter, Gordon. That's amazing. And probably even in some of the ones that were before, it was really a workshop. So that's exciting. Okay, so we're excited to be here, 30th annual workshop. Just quickly, this is what we're going to be doing. We have 3 fun presentations by Jerry, a tribute to Warren Washington. Peter is going to give us a history of one of the first simulations we've done way back at the beginning of this effort and 30 years ago. And Cheryl Craig is going to talk about a day in the life of a CSM developer from 30 years ago or so. I know these are all going to be super fun. And then we're going to have the inaugural, and I'm not sure if this is going to be repeated, but definitely excited to have the Outstanding CSM Community Service Award, because the word community is central to everything we're doing here, and you guys are all here because of this community, and we want to recognize someone, an individual who's represents that. And then we're going to have a roundtable discussion with former CSM chief scientists, and then we have food and drink and music. And Nan Rosenblum, is she in the room, or she's prepping, I guess. She's NCAR staff. Her band is here, and so that's going to be super fun after this. So, and this is the list of former chief scientists. So we're going to hear from all of them. That's going to be super fun. And again, I'm really humbled to be standing here in front of all of them at the beginning of this. So we're going to start off with Jerry. So Jerry, please come on up and give us your tribute to Warren.
Thanks, Dave. And so this, as you indicated, this is going to be a tribute to Warren Washington's pioneering work in Earth system modeling and CESM. And as most of you know, Warren, NCAR climate modeling pioneer, passed away last fall. This is the first CSM workshop since his passing, and so because he played such a critical role in the history not only of CSM but history of Earth system modeling and climate modeling at NCAR, we thought this would be a really good time to dedicate this session to his memory. So that's what I'm going to talk about, and then as Dave said, Peter's going to say a little bit about early CSM simulations. So Warren came to NCAR in 1963, and he was he really was on a mission to build an atmospheric general circulation model. And the idea was numerical weather prediction was a big thing in the 60s. And so when he got to NCAR, he met another scientist named Akira Kasahara, and there's a picture of them on the right there. And they said, okay, well, let's put together a general circulation model of the atmosphere. And they called it the NCAR General Circulation Model, not surprisingly, or the NCAR GCM. And so there's a few pictures, early pictures of Warren in action. The lower left is a picture that's shown a lot. Warren's actually holding up a strip of microfilm. And microfilm was the way you looked at your plots that came out of the model in the early days. It was a DD80 photographic printer, and you got these, and Cheryl's going to talk about this in her talk, you get these little boxes with microfilm reels, and you'd see NCAR scientists in this pose that Warren's in the center there at the bottom, staring at the prints that are on the microfilm reel frame by frame that you run through the reader, and then you can make little prints of them, and you see a print of one of the frames coming out there at the top. And so that's how you looked at your output from the model. Things got a little better with workstations. There's Warren in the early 80s with John Humbrecht, who was a software engineer then, with one of the workstations. But Gary Strand has a great story of how they used to do animations, because you'd actually take a 16mm camera, set it up in the Damon room, or maybe the director's conference room, and aim it at a workstation and bring up a frame of the model output from the workstation, click one frame of the 16mm camera, advance the image on the workstation, click another frame on the 16mm camera, and that's how you made animations of model output at that time. Things have gotten a little better since then, luckily. So this line came for this do something different line came from Akira Kasahara's autobiography, and he said when they started thinking about this at NCAR, they wanted to do something different, and basically different to what was being done at GFDL, because GFDL was the big powerhouse in modeling at that time, and they wanted to do something that GFDL wasn't doing, and so they wrote this line. Warren actually wrote this line. The first line in the abstract of a tech note from 1975 when he was looking back on the start of their modeling effort together. Quote, they wanted to make the model available to the atmospheric science community as a facility for numerical experimentation, as well as to fulfill a need at NCAR for studying the large-scale dynamics of the atmosphere. So from the very beginning, this is early 60s, they were thinking that this model would be a community resource and a facility. And we heard Everett yesterday use that same word, facility. The CESM is a facility for the community, for the university community. So right from the beginning, they had this vision of what a community modeling effort at NCAR should be. So they came up with the first version of the model. The first generation NCAR GCM, they called it, was in 1965. They ran it on a CDC 3600. And Betty was pointing me to some of these references, and we realized that 2025 marks the 60th anniversary of community climate models at NCAR. The first one was 1965. And so we're celebrating the 30th anniversary of CSM, which is the most recent incarnation of these community modeling effort, but it goes back to 1965. And of course, it evolved from atmospheric-only models to coupled models to current CSM Earth system models. So they kept coming up with new versions. The second generation version came out in 1968, the third generation in 1972. And because it was a community resource, university scientists were getting interested in using the model. And to use the model in those days, that meant you had to physically come to NCAR, because you had to submit a card deck. Each card was a line of code, and you'd submit the card deck, and that was the model, and they'd run it through the card reader, and it would run on the computer, and you get your output on microfilm. So scientists had to come to NCAR to run the model. So you had this community of scientists that would show up every summer, and they started having these informal meetings. And I got to talk to Dave Williamson about exactly how this evolved, but they would have these gatherings of GCM users that later evolved into a users group meeting. But by the mid-70s, this was getting to be a kind of a big thing, and they realized they needed to have more organization, so they formed something called the GCM Steering Committee. It was chaired by Francis Bretherton, And when you read the mission of that committee, it basically reads exactly like the mission of the current CSM advisory board. So already in the 70s, all the pieces were in place for what ended up becoming this effort, now the CESM. Then there was a significant development in the late 1970s. A group of Australian scientists had developed something called a spectral model, a spectral atmospheric model, and this meant that you were not computing the equations on grid points, but you're computing them in wave number space. And so they devised this atmospheric model, they brought it to NCAR, and it became the basis for a new NCAR atmospheric model called the Community Climate Model, or CCM. So 1979 was the CCM-0A, 1981 was the CCM-0B, and this is a great line from a paper Dave Williamson wrote reflecting on the start of CCM-0B. It was intended to be a combined forecast and climate simulation model. And this is a quote from Dave's paper. They wanted to utilize the same basic code for global forecast studies, both medium and long range, and for climate simulation. Economy and increased efficiency could then be achieved by documenting and maintaining only one set of codes. So this sounds a lot like seamless prediction, which is what we're still talking about. So even at that time, they were thinking in terms of using the same model for numerical weather prediction and climate. By the mid-'80s, there was CCM-1, and they started holding these annual summer CCM workshops as the demand continued to increase. And so the number of participants continued to increase, and so increasing attendance became a concern, because there was concern that they wouldn't be able to fit all the CCM users into the main seminar room or any meeting room at NCAR. And so they were talking about maybe they'd need a bigger venue. And of course, this foreshadowed the move to Breckenridge for exactly that reason 15 years later. But Warren was giving a talk about this in the early 80s, and he was, it may have been a Board of Trustees talk, but he was talking about the future of CCSM, and there's going to be ever-increasing numbers of users, and we're going to have to move to a bigger facility that's going to accommodate all these many users of the model. And so he used this graphic to illustrate what he thought would be a good venue. And this is typical Warren Washington humor, right? So let's put all the CCM users in Mile High Stadium, home of the Denver Broncos. But it wasn't far from, it was actually far from the truth in terms of numbers, but it was actually the concept of increasing numbers of users was definitely happening. And this is a shot from an early CCSM workshop in 1987. See these kind of bizarre little workstations, and by then it got away from cards. You could actually submit your code electronically. You see Warren there in the back right, and some of the other early luminaries there of the atmospheric modeling effort. You see Randy Dole in the front left there, who became a prominent NOAA scientist. Dave Erickson's in the front center there, who became an NCAR scientist later. So all these people were filling up the Damon room, and this is kind of like what the tutorial kind of looks like in some form in the present day. But I'm kind of getting ahead of myself here because we're talking about Earth system modeling. So let's go back to Warren's interest in Earth system modeling. So in the late 70s, Warren got interested in this, partly because Suki Manabe, GFDL, was already doing it. And this was the usual NCAR GFDL competition. And Manabe had teamed up with Kirk Bryan, an ocean modeler who had a coarse grid ocean model. And they were running something called a sector coupled model. And they had 120 degrees of longitude as a sector. One strip was land, the other strip was ocean, and then the atmosphere kind of covered that whole sector. And they were able to run coupled with that kind of idealized geometry just for the northern hemisphere, and they got it to run. But Warren wanted to do one better than that. He wanted to run with realistic geography, a global model with the interactive components of atmosphere, ocean, land, and sea ice, but he needed a more powerful supercomputer. So the first supercomputer defined as using vector processing was the Cray-1. It was invented by a guy named Seymour Cray in 1975. NCAR bought the third Cray-1 off the assembly line, serial number 3. The first two went to DOE labs to do classified bomb research, supposedly. It replaced the CDC 6600, which was also designed by Seymour Cray. And here's some pictures of the early kind of evolution of the Cray-1. That upper left picture, it's kind of like evokes the image of the Marines raising the flag on Iwo Jima, right? You got these engineers shoving the Cray-1, the supercomputer, the fastest computer on the planet, into the basement at NCAR to get it into the computer room. There's upper right is Warren posing there proudly next to the Cray-1, which is going to allow him to run an Earth system model. And this Cray-1 was a really weird looking thing. In the lower right there, you can see it was kind of this circular thing that all the the circuit boards that had the chips on them were in those kind of vertical stacks. You could stand in the middle of the supercomputer if you wanted to, like this software engineer is doing. It had these kind of weird padded seats around the bottom that actually were covering big transformers that were handling all the electricity that was coming into it. It looked really like something out of a set for Star Trek. It kind of had this really otherworldly, weird, fake look to it. But it was the most powerful supercomputer on the planet. It was about 80 times faster than the 6600. And to give you an idea of how computing power is advanced, and there's various estimates on this, one estimate is the iPhone you're carrying around with you is about 7,000 times faster than the Cray 1. That's how far we've come with computing. But in 1977, this Cray 1 was a big deal. It cost $9 million, which is about $50 million today. And this would allow Warren to start running the first Earth system model at NCAR. Even with this fastest supercomputer on the planet, you still couldn't synchronously couple and have the ocean atmosphere communicating as the model ran. You had to divide it up in some way to allow it to be able to run at all. And so they came up with something called asynchronous coupling. And asynchronous coupling meant that you ran the atmosphere for 4 months, January, April, July, and October. Those are just 4 monthly simulations. Take the fluxes from those 4 months, fit a second harmonic to them so you get 12 monthly values, then give those 12 monthly values to the ocean, run the ocean model for 5 years. In the 5th year, you take the sea surface temperature and sea ice distributions from January, April, July, and October, give those back to the atmosphere. The atmosphere runs those 4 months, January, April, July, and October. Second harmonic runs through it, get 12 monthly values, give it back to the ocean, and it goes back and forth like that. And they were able to run 4 cycles with this kind of configuration. So Warren had expertise in atmospheric modeling. He connected with Bert Sempner, who was an ocean modeler at NCAR, and he had a coarse grid ocean model, and so they were able to put together the first, what was then called a coupled model, which we now call an Earth system model. Had realistic geography, it was a global model, had components of atmosphere, ocean, land, and sea ice. It was run asynchronously without flux correction, and produced a credible, at least for the time, simulation of the Earth's climate. And this paper was published in 1980. And I found this picture on the right there. Bert Sempner's on the left, Warren's in the middle, and I'm on the right. I was a very, very early career scientist. And I was basically amazed to be able to be working with these two really pioneering climate modelers as they put together something that had never been done before. And this was really exciting because this was something that I didn't think I would ever get involved with, but it was really exciting to work with Warren and Bert on this model. Well, this is what came out, and it looked like planet Earth, which was a good thing, right? So you look in the upper left, that's zone mean temperatures from the atmosphere. The models, the 2 panels on the top, the observed are the 2 panels below. Looks roughly like the observations the model does. If you look at ocean heat transport from the ocean model in the lower left there, the ocean was transporting heat northward, north of the equator, southward, south of the equator. That's a good thing. Look at the sea surface temperatures there, kind of in the middle panels. The computed sea surface temperatures on the top, observed at the bottom. Tropics were too cold, high latitudes were too warm. It was a very diffusive model, but there's some sea ice was able to stick around there in the Arctic, so that was a good thing. We're looking at ocean currents, and you see the gyre circulations from the computed currents on the top there compared to the observed at the bottom. So this was considered to be a success because the model didn't blow up. We got something that looked like Earth, and so this was a good step forward to benchmark subsequent efforts. But even in the early 80s, it was still too expensive for Warren to run fully synchronous global coupled models, especially for the climate change work that he had gotten some funding from DOE to do. So a number of workarounds were devised. One was running the atmospheric model with a surface energy balance, or swamp ocean, which would come into equilibrium very quickly because it's just to have a surface energy balance like a wet surface. A non-dynamic slab mixed layer ocean, which we're still using versions of that type of configuration today. You could get double CO2 and get that to come into equilibrium in like 30 years or so. But then finally, NCAR got another new supercomputer, the Cray XMP. It arrived in 1986, and then that allowed Warren to run a fully coupled global Earth system model, synchronously coupled, without flux correction, for an increasing CO2 run for decades. And 2 experiments were done, an instantaneously doubled CO2 experiment and a transient experiment, which is kind of a new thing, a new wrinkle for the field, where you had CO2 increasing at 1% per year. And that was published in 1989. And that model, the NCAR model, was that put NCAR in the kind of the head of the line in terms of international global coupled climate modeling, as evidenced by these 4 plots here. These are climate change plots from the 4 modeling groups in the time of the early 90s that were doing these experiments. This is a figure from the 1992 IPCC update to the first IPCC assessment report. GFDL at the upper left, Max Planck from Germany in the upper right, NCAR lower left, and UK Met Office in the lower right. And you look at the patterns of temperature change, and some of these things still look familiar, right? So if you look at the Arctic is warming faster than anywhere else. High latitude warming is something we're actually seeing now in the real world. Land's warming faster than the oceans. Southern oceans were kind of warming less than anywhere else. So even in these early attempts at global coupled modeling, you see some of the things we still are seeing in models today. So CCSM, or the acronyms, Peter's going to sort all the acronyms out. Whatever turned into CESM, started in the mid-1990s, which is why we're celebrating this 30th anniversary year. And when this was kind of getting going, Warren was actually leading work on the use of the massively parallel computer environments in the late 1990s. And this ended up being the DOE NCAR Parallel Climate Model, or PCM. And the reason that Warren did this was that Dave Bader, who was our program manager from DOE, said, you know, if you guys can come up with a model version that can run on massively parallel computers, I can get you a ton of computer time at Los Alamos. And we said, great, you know, this is really going to be great for us. So with some coding and recoding and to get it to run, we were able to run the parallel climate model. And before then, the vector architecture on machines, you just run everything on a long array of data, but on parallel machines, you distribute the computations between thousands of individual processors. And this step forward into parallel computing was summarized by Andrew Weaver in a quote from a paper he wrote a number of years later. Moving from vector to parallel codes opened up a whole new realm of possibilities. It allowed for better representations of the physics to be incorporated, higher resolution models to be run, and for those same models to be run for longer times. Parallelization was revolutionary for climate science. And so this was going on as the CSM, or CSM, whatever it is, was being developed, and these two efforts ended up being merged around 2000. So the scale of this effort is kind of interesting to look back on. I mean, you look at this room full of people. The Earth System Modeling Group, which we didn't call, it wasn't called that, it was called the Climate Change Research Group. It was at NCAR, looking at climate change coupled model simulations. There was 4 of us in 1989. Myself on the left, Tom Betke, Linda Verplank, and Warren. This was the extent of the DOE-funded climate modeling effort at NCAR. It expanded in 2005. This picture on the right is the Climate Change Research Group at NCAR. And you can see some familiar faces in there. Of course, Warren's on the left. I'm there. Haiyan Tang is third from the left. Gary Strand is in the back row there. Stephanie Shearer in the front. You see Dave Lawrence in the center back there. He was part of the DOE-funded effort doing climate change research. Vince Whalen, Julie Arblaster in the front. Reto Canuti in the back row there, getting toward the right. Aishu Hu and Lawrence Buja. So that's how this has been growing ever since, and it's gotten to be a bigger and bigger thing. And then, of course, CSM, or CSM, or whatever you want to call it, came along in the mid-90s. And Warren ended up being a co-chair of the CSM Climate Variability and Change Working Group. Actually, it started out being Climate Change Working Group, and then it was merged to become the Climate Variability and Change Working Group. And he was a co-chair of that group from 1999 to 2015. And before that, he was CGD director from 1987 to 1995 during the formative stages of the CSM. So if you look at these pictures on the left, this one on the upper left, I don't know where I got it. It's a poor quality photo, but it was from the second Breckenridge workshop in 1997, out on the patio there of the village condos. The reception is myself, Bert Sempner, John Weatherly, and Warren. The lower left was from the 2007 CCSM workshop at Breckenridge. There's Warren with Jay Fine from NSF. He's a program manager from NSF, and he played a critical role in his support for this whole CCSM effort. And it was really his support that made a lot of this possible. So Warren was influential in the community modeling effort at NCAR starting in 1965 all the way through to using CSM in concert with the DOE funding at NCAR. And here's a few more pictures. In the upper left there, anybody that was at one of the Breckenridge workshops recognizes the dreaded 10-mile room. This is this massive room where we had all the plenary sessions. It was also the room where the roof collapsed due to excessive snow cover, which then shut down our visits to Breckenridge for the CSM workshop. But that was the scene from the plenary. You can see and this is a picture that somebody took at the dinner in 2007. That's Warren and Mary on the left there, Kevin Trenbrith in the center, Rick Rosen and Phil Cameron Smith, and Warren and Mary on the right there in Breckenridge in 2011. So to kind of sum up, Warren was a pioneer in Earth system modeling at NCAR, first with the community atmospheric model in the 60s and 70s, then the first NCAR Earth system model in the 80s, then the PCM in the 90s, and CSM in 2000s. And Warren's legacy lives on today in the CSM effort that we're here talking about this week. Thanks.
Thank you, Jerry, for that excellent tribute, and obviously you showed us how much we owe to Warren and what we're all able to do here. Without him, who knows where we'd be. So next up, Peter's going to sort of talk about, I think, the birth of CSM and CSM.
You'd advance it by one of these things. Big button. Okay. Can you remember what you were doing 30 years ago? I only just can, but I'm here to talk about what we did close to 30 years ago. We did this thing called the CSM run. It went for 300 years. So in 1995, a group from the Climate Division, the Atmosphere and the Ocean Group got together and started coupling models that they had. But in early 1996, each of those groups had a new version of their model. The Atmospheric Group had a new version of CCSM3, Community Climate Model 3, and it was called a climate model, even though it really was only an atmosphere and land. And they had this new version with a resolution of T42 times 18 levels. T42 is a resolution of around 2.8 degrees. The land component, land surface model 1, ran on the same grid. And the ocean section had a new ocean model called the NCAR CSM Ocean Model, NCOM. Its resolution was 2.4 degrees zonally, and meridionally, it was 1.2 at the equator, up to 2.3 degrees at higher latitudes, and it had 45 levels. And there was a sea ice component called CESM. This ocean component we were all proud of because it had two new parameterizations that had been developed in the ocean section. One was a new vertical mixing scheme called the K-profile parameterization, KPP, pioneered by Bill Large, and a new parameterization of the effects of mesoscale eddies that weren't resolved in these models at about 1 degree. So the mesoscale eddies were determined not only to diffuse along surfaces of constant density, but the new feature was that they had an effect that was also due to advection. These were new, and we were proud of this, and we finally put it in this new model with higher resolution than we'd used before. So we put these together. No changes of any parameters from what the atmosphere and the ocean model had set up as their best versions of the model. We ran for 10 years, but unfortunately, the land component didn't have a river runoff scheme. So all the net precipitation minus evaporation that was occurring over land was lost to the system, wasn't going back into the ocean. So the global average salinity in the ocean was rising quickly, and so the run was stopped. And we had to decide what to do. And I sort of vividly remember an afternoon meeting when we all got together and said, what are we going to do? We thought that producing a river runoff model that none of us knew how to do would take many months, 6 at most, probably a year, and we didn't want to wait that long. So we came up with a scheme that in fact took a day to implement. We multiplied the precipitation from the atmosphere by a time-varying factor which was determined by the globally averaged evaporation divided by precipitation over the ocean and the sea ice. This meant that we increased the precipitation from the atmosphere to the ocean instead of producing river runoff. The advantage of this was that this was the simplest thing we could do to ensure conservation of water. But the trouble was that fresh water was going into the ocean, not where the rivers came out into the ocean, but it was basically in the areas of the ocean where the precipitation was highest, so basically in the intertropical convergence zone. But it did conserve water in the model. And in my view, the best way to characterize that is it should be viewed as a very poor river runoff scheme. So, in May 1996, which was the date of the first meeting in Breckenridge, where we were there in May, where what we remember most is it snowed, and there were only 2 restaurants open because all the others had closed. So we had trouble finding something to eat. But in May 96, the run was restarted, and it ran at about 2 years per day on the Cray YMP. And we stopped after 300 years, which was, I think, in October 1996, because the salinity distribution in the ocean had got really poor by then because of this factor of what we were doing. It was becoming too saline, where the Amazon should have been coming out, and not nearly saline enough under the intertropical convergence zone. But to our, I think, correctly described as a complete surprise, the surface temperature of this model adjusted in the first 10 years, but then after that, it maintained pretty much the surface temperature of the globe. In fact, if you look at these in the averages are drawn in the lines from the years 10 through 290. There is virtually no drift in that globally average surface temperature. And in fact, if you wanted to, you could pick particular years near the beginning and the end of that run where the global drift was precisely 0. The drift was something in this one we did as something like 0.02 degrees per 100 years. So this completely surprised us. Most groups, not NCAR, when they put together their models, couldn't maintain this surface temperature. And they had to use these flux adjustments, which were arbitrary fluxes of heat and fresh water between the atmosphere and the ocean in order to maintain a current day surface temperature. So this we all thought was a big deal. So there were some subsequent events that I want to describe. Byron and I were the nominal heads of this, one from the atmosphere, one from the ocean group, but really we were all in this sort of together. But Byron, Beauville, and I wrote up a short paper on this CSM1 run, and when you got a big deal, you submit it to science. it was rejected because one reviewer said we'd use salinity restoring in the run. Sea surface salinity restoring had been used in the ocean spin-up run, but not in the coupled run. In fact, when I think about it, if we'd used salinity restoring, the salinity field would have looked a lot better than it was. We probably could have run this for more hundreds of years, because if the salinity had looked better, we probably wouldn't have stopped it. But we didn't. We wrote back to the editor that the reviewer was incorrect, but he still rejected the paper. So the first paper that I ever had rejected was what I think was my most significant contribution to a real science in my career. I've only had a couple other things rejected, but this was the first, and I think it was the most significant result of my career. That expanded paper was then published in the Journal of Climate in June 1998 as the first paper in this June edition. And as you can see, it's reasonably thick, and it contained 20 papers that were all describing this CSM1 300-year run. I think because it was such a big deal, the editor, chief editor there, Dave Randall, thought it appropriate to have a whole issue on this CSM1 run. First time that I think had ever happened. There were more subsequent events. Some were subsequent after others. So, at the next annual workshop, we heard a rumor that really the CSM1 run went for 350 years and the climate had gone off the rails. So we chose to conceal this, ignored the last 50 years, and only showed up to 300 years. Thinking about it now, I think this is the first time I came up against a conspiracy theory. This, let me assure you people, was fake news. We stopped the run at year 300 because the salinity distribution had got so bad, and we did not run it beyond year 300. The next thing we found out was that Jay Fine, already mentioned as our chief sponsor, program manager at NSF, told us that the then GFDL director had written a letter to him saying that we must have cheated in some way because all climate models needed flux adjustments in order to maintain the present day climate. Now, I don't know about others, but I never saw this letter, but Jay Fine assured me that he had it, and he asked us, had we cheated? And we said, no. We put those models together with our best parameterizations for each component. We put them together, and it ran, and we didn't need flux adjustment to maintain the present day climate. Incidentally, that GFDL director, when he left GFDL, came and bought a house in this region. And UCAR immediately hired him. But he apologized to us for actually writing this letter. So that confirmed that this letter was indeed written. So, in conclusions, this run was the first long run to maintain the current temperature climate without the use of flux adjustments. I still think it was a pretty big deal. Maybe we were lucky, maybe we were Good. It was due to improvements in both the atmosphere, but I think also especially the ocean component. Those two components that I talked about, KPP and eddy invection, have been used in many, many models since. In fact, when I look it up, between them, those two papers have 6,300 citations. So they've been used a lot. The next group to do something about it was the Australians. They put together a new ocean model that had those two parameterizations in their climate model, and that reduced the required flux adjustments over the Southern Ocean by a factor of 10. The flux adjustments over the Southern Ocean in their model originally were somewhere between 250 to 300 watts per square meter. That's because it had a significant improvement south of the ACC and in the Southern Ocean. They put together a new version, and when they found out what flux adjustments they needed, they were more like 25 watts per square meter. But they didn't actually, they still used flux adjustment. So the next group that used a non-flux adjustment version was in fact the Hadley Center. It was the next non-NCAR group to run without flux adjustments and maintain the present day climate, and they did that in the very late 1990s, around 1998, 1999. And then in the 2000s, most other climate modeling groups started to run models without flux adjustments and maintain the present day climate. This, I still think, was quite a big deal. So thank you for your time.
Thank you, Peter. That was fun. And I thought one of the most controversial things was that the first workshop was in May. We don't do the workshop in May. The workshop's in June. So, okay, so last up, we have Cheryl Craig, and she is going to talk to us about technology. And also, she's a software engineer, and just want an opportunity to recognize the massive contribution of all the software engineers into the CSM effort. So it's really great to hear from Cheryl about her experiences, her early days as a software engineer here at NCAR.
Well, thank you all. I have been in NCAR since since 1980. But I've not been working on CESM that long. But these are memories that I have of my early days of working at NCAR. So what I want to do is, we always talk about how supercomputers have enabled us to do our CESM model. You know, we've brought in a lot of extra physics, we've increased the resolution, all this wonderful stuff, and it's all because we've got supercomputers, right? But there's also other things that happened that if they didn't happen, we wouldn't be here today. So let's take a look at what a typical day of using the technology of the 1980s and early 90s, what that would look like for us doing our CSM work. So this would be just prior to that first NCAR or CSM workshop. So when we head into work, I don't know about you, but one of the first things I do is check my email. What's come in? But email didn't exist. Before there was email, there were memos. Okay, if you look at this, it pretty much looks like an email. You know, it's got the to and the from and the date and the subject and then what's being discussed. But it's on paper. So this is how things came to you. So, you know, if a head of a group wanted to send out an email to everybody in the group, they'd send it to the secretary or to the division director. And the secretaries, that's what the admins were called back then, they would stamp on the top of the memo the date that it was received. And then they would go to the copy machine and they'd make copies for every single person in their group. Then they'd put it in your mailbox. So you went to your mailbox, your physical mailbox, several times a day to see what memos had come in. Well, even phone calls were more complicated. NCAR had one phone number. So everybody that was being called came in on one phone line. The switchboard operators answered the phone, said, oh, you want to go to extension whatever. They would transfer the phone to your personal desk phone. But there weren't answering machines on these phones. So if you didn't answer a call, after a certain number of rings, it went back to the operators. They had a list of, here are the secretaries associated with this person. They'd send it off to one of the secretaries. She'd take a message on a piece of paper like this, leave it on your desk, and that's how you found out who called while you weren't at your desk. Okay, so now we're done reading our emails. We're done with our phone messages. It's time to work on CESM. But there's no personal computer. So instead, you submitted your code on Fortran punch cards. So at the top of the card here, it does say, let's see, here we go. You can see this is the line of code that has been punched. And you don't have to read the punches, that's what the machine does, so you could actually read the top of your card. It was one card per line of code, and it had an 80-character limit. But you didn't even get 80 characters. The first 5 characters were for labels, and labels were used extensively because we didn't have modern structures like while loops and do loops. You had go-tos, and they used a label to tell what line of code to go to. The 6th column was for continuation. So if your line of code went more than the 80 characters, column 6 had a comment or had a character in it, and that indicated to the computer this is still the same line of code. So basically, you had 66 to 74 usable characters that you could use for each line of code. So how you would do this is you'd sit at your desk, you'd write out your program, and then you would carefully punch out your punch cards. Now, every typo, once you type something and it says an S and you meant a T, that card went into the discard and you started over. So you typed it very carefully. So there was a room in the first basement in NCAR that was filled with card punch machines. And if you look here, you can see here is the deck of unpunched cards. So you could go grab some of those unpunched cards, put them in your machine, and then use that to punch the cards for your card deck. Now, a typical program was either grouped together with a rubber band, or if you had a big program, you'd put it into a box. And if you wanted to change some lines of code, you had to go to your box of cards. You'd look for, okay, that card that said, you know, the wrong thing, and you pull that card out, you'd put your new card or cards in. So card decks, you took downstairs to the first basement to where the computer room was, and you'd come back maybe in an hour or 2 later to see if it was done. And you were lucky to get a handful of jobs done. How many of us, when we submit a job to Rachel, we sit there and we go, is it done yet? Is it done yet? Well, back then, you actually physically walked downstairs to say, is it done yet? No, I've got to go walk back up and come back later. So code lived in your card deck. That is where it lived. Once you submitted your deck of cards and you got your output out, it didn't exist in the supercomputer anymore. So you kept track of that deck of cards. So your output was given to you in a computer printout. And this is what they looked like. This is actually a copy of one of my programs that I wrote back in 1984. I didn't want to keep the deck of cards, so I actually printed out what the program was, just to archive it. Okay, so how many boxes of punch cards would it take to store all of the atmosphere model CAM or CESM? So CAM's about 1 million lines of code. CESM is 5 million. Okay, so you would be taking 515 boxes of cards downstairs to run CAM, or almost 2,500 boxes to run CESM. Remember, you get to haul this up and down every time you run. Okay, as NCAR got wired for networking, cards were replaced with VT100 terminals. These are simply dumb boxes. They had absolutely no processing power, and they were a shared resource. So if you wanted to do some editing and you couldn't find a VT100, you went and did something else. But basically, it was a keyboard, a monitor, and a network connection. That's what it was. Okay, if you wanted to share data with somebody external, you used 7 or 9 track tapes. You got to work out, this thing is heavy, okay? Most of the time, you needed more than 1 tape. So your arms were really good for carrying tapes up and down. If you wanted to protect for reading and writing, you had these write protect rings, and I can't remember whether it's put it in or take it out. But you would put these in or take them out, depending on whether you wanted to read or write. You had these floating all over your desk drawers. So they were 6250 BPI tapes. They were the best tapes out there. They held 175 megabytes of data. They took about 6 minutes to read or write this entire tape. So the operators would take the ring off, and then your tape is inside. Now, tapes were stored down in the racks in the computer room. So if you remember that picture that Jerry had with the Cray 1 at the front with the guy standing in the middle, if you looked at the back, that whole back was this tape storage area. Okay, so let's take a look at a recent run that Cecile made. This isn't even a big run. This is just kind of a modest run. It's a 1 degree, atmosphere only, 20-year run. It's not even fully coupled. She used almost 125 gigabytes of data and produced 428 gigabytes of output. Okay, so let's say all we had were these tapes to run on. So she would use over 3,000 tapes. The stack of that would be almost as high as a giant sequoia. Now, it would take 324 hours just to read and write. It's almost 13 and a half days. That is not counting that the operator has to come, find that tape, put it on the rack, and then you could read it. So it would have probably doubled or tripled that estimate. Okay, so your run is finally done. Now it's time to visualize your data. But of course, personal computers didn't exist, and graphic packages were in their infancy. So you used a tool like NCAR Graphics. It was known as Autograph in the early days. It was black and white, as we've seen from the plots that were shown, and it evolved to color over time. And as was already mentioned, output came onto our microfilm. So it was a string of plots. If you wanted to see that 50th plot, you had to zoom through 49. You probably overshot most of the time. You had to go back. But that's how you would find the plots you wanted. Now, microfiche was something that was a little easier to eyeball. You could at least see, well, that's the plot I want. So you can kind of zero in on where you wanted to go. And then as we got color, they came out with color slides. And they were nice because you could eyeball them. And what was really nice about them is if you wanted to save a slide, you could just pull it out and save it. And this was replaced by digital storage pretty quickly at NCAR. So there were special viewers to view microfilm and microfiche, and the library had a number of these viewers that you could use. And then, as Jerry mentioned, if you wanted to make a printout, they had thermal printer paper that would print out. But it was really kind of a bad quality, and if you left it on your desk and the sunshine came in and hit that paper, it would turn all black. So you needed to physically store all your graphical output. So the microfilm was in a box like this. The microfiche was in a paper sleeve, and then color slides were in boxes like this. So if you wanted one picture off of this to save for posterity, onto your bookshelf it went. If you wanted to tweak a graphic out of this microfilm and make one change to one plot, you get a whole nother realm, a whole nother reel to keep track of. So a side effect of all this paper, non-digital age is you needed to physically store everything. You can see this in the evolution of my office. I've got several file cabinets that are full of things. You know, this printout came from that file cabinet. Nothing from the last 10 or 20 years is stored in them because it's all stored digitally. Okay, we're at the end of the day. We've gone home. We want to check on something on the computer, but there's no internet. So you needed to use a modem. Now, a modem would tie up how many of you recognize that sound? So a modem would tie up your phone line, your single phone line into your house. So you had to get all your kids off. You had to negotiate with your spouse that you could use the phone line, and then you could call into work. 300 baud modems were economical, but they were really, really slow. It's 300 bits per second. So 1200, 2400 were nice upgrades. Now, another thing to consider is that if you lived where it was long distance, so Longmont, which is just 10 miles down the road, was long distance to NCAR. So not only did you get to call into work, but you got to pay long distance charges to call into work. So there were two big technology advances that I think got us to where we are today. And I really think that without them, CESM as we know it would not exist. And they are the personal computer. Digitally, we can store everything on there. We don't have journal articles in file cabinets and drawers of them. We can go and we may have collections in our directories on our computers, and we can find them pretty quickly. And then the internet. We can electronically share information with colleagues all over the world. We don't need manuals on our bookshelves to look up, well, what is the Fortran definition or statement for this? And where would we have been without Zoom? I mean, we've used it for this meeting. We used it during the pandemic. It's a way that we just can share with people worldwide. And without the internet, it wouldn't have been possible. So without all the advances in technology, CESM as we know it would not exist. And while technologies improve the way we write and debug our programs, store our data and program files, display our results and work from home, there's one thing that I think still has remained the same. And that's writing code can be very frustrating at times. This cartoon from 1998, I think, is as relevant today as it was back then. So thanks for listening. I welcome any questions or comments. And as a side note, I asked ChatGPT to put together this collage. I specifically said, put in Fortran punch cards. I did it several times. It never showed up. ChatGPT doesn't know what I'm talking about.
Thank you, Cheryl. That was
Sure.
excellent, really fun. Can you go back, Kelvin, to our presentation? Okay, great. Thanks, everyone. That was a lot of fun, a lot of walk down memory lane for some of us. Right, so now we're going to go on to the new outstanding award for community service, but I just wanted to put up this as another way of sort of visualizing the time history of CSM. These are the award winners for the CSM Distinguished Achievement Award. 25 years of that, so we started doing this award in 2001, and I'm not going to read through all the names here, but it's fun to just see, who is involved in the CSM activity over the years. And all these, not all these, but most of these are reflecting contributions, scientific contributions, model development contributions, or software engineering contributions, but there's nothing on here that really captures, the community aspect of what we do. And so that's why we introduced this new award this year for the Outstanding Community Service Award, and it will recognize one or more people for the dedicated service or support to the CSM research community. And I'm going to try to build tension here by not announcing it, but just describing this person. You guys will get it very quickly. But this person embodies everything that the word community in CSM stands for. She works tirelessly to support the development of the coupled model, helping and shepherding the development team by managing and tracking the always growing set of simulations and analysis as required. She is passionate about enabling users of CSM and is one of the driving forces behind our CSM tutorial activities. In particular, she is one of the leads of the CSM Tutorials on the Road activity at AGU, AMS, and other venues like the WC conference in Kigali in Rwanda. She is always ready and eager to help anyone who needs help, and now she is leading our efforts to develop robust end-to-end workflows for CSM to make the lives of all CSM users easier going forward. So you guys have all figured this out. The award winner is Cecile Hane. We have this beautiful award. So I'll just say I'm proud to have Cecile as a colleague, and I cannot think of anyone more deserving of this award. So congratulations, Cecile. Okay, thank you. So now we're going to move on to the former chief scientist. So all the chief scientists, please come up and here sit at the table, and John is going to then take over this sort of roundtable discussion.
Dave's done so much already that I thought it was reasonable that he could have a break now. So he's not one of the chief scientists around the table, and he's sitting down there. And I wonder whether we ought to just thank Dave for all the work in putting this together, because this session and the whole meeting wouldn't have happened without him. I think we have some slides. So we're going to go through, these are all the chief scientists, and the one we haven't got with us today, because he's not with us anymore, is Byron. We heard a little bit about Byron in the talks, and I have one story about Byron, because I knew him when I was here the first time around, and he basically said, I work miles more, he was talking about the time cards that we had to fill out. And he said, I work more hours than this. You have to put in 80 hours for the 2 weeks that were done. And so he entered one with 160 hours and then got paid for 160 hours. And then spent a long time trying to correct that process afterwards, basically. But I also wanted to just see if Jeff had got any recollections he'd like to make of Byron as well, because you were around.
Yes.
I think you might have to hold it.
Oh. Yes. I first came to NCAR in 1978. Byron came a little later, and I can remember the day that he walked down the hall to my office and said, how would you like to learn how to run a GCM? And I learned how to, I was very reluctant to do it, but he tutored me in running the model, and we became very close colleagues. At that time, we were both working in the stratosphere, simulating the stratosphere, and worked very well together. Byron could be quite volatile at times. So we all had to accommodate that. But I think in retrospect, thinking back in the selection of Byron as the first chair of the Scientific Steering Committee, because I was a possible candidate for that at the time, it was the best choice. Because Byron not only had a tremendous expertise in science, atmospheric science in particular, atmospheric dynamics, but he had an incredible knowledge of computer science and what it took to couple two models together, and all of the expertise that was required working with software engineers and scientists. So he was a perfect choice for that and shepherded the SSC quite well. And I think we should all be thankful for Byron's tremendous contributions and efforts to this community model.
Thanks, Jeff. So now we're going to go along the line, and I think we'll see some. I'm not sure these are current pictures, but we'll and as we go around, I'll ask you to kind of introduce yourself and answer question one, which you're aware of, which is some interesting and poignant and potentially funny moments during your time as a chief scientist. And let me start by saying that actually my first ever job was at NCAR in CGD, and my first ever boss was Jeff. So I got my first job from him. So, and let me also, before I hand over to him, say happy birthday in front of everyone. He's given up his birthday to come and tell you a story. So over to Jeff.
Well, thank you, John. I was also Cecile's first boss. So, you know, there are a lot of stories I could tell, but I can't. There's the infamous conga line dance at one of the Breckenridge meetings that even a UCAR trustee was a participant in. But yeah, I thought about this a lot in terms of funny stories. What I would like to take the time to talk about is, and Dave mentioned this, you know, we're all sitting up here as chairs of the SSC, but I think many of you know, and many of you have been part of this, tremendous amount of work, tireless work by so many people over so many years to make this modeling effort a success. And it wasn't clear it was going to be a success. And here's a little story that I can tell. There was a handful of us went up to the director of NCAR at the time to propose that we do this. We take this on. We couple atmosphere, ocean, ice, land, and get a coupled model running. It would be a community effort, be open to the community. And it was Bob Serafin at the time, and Bob said, okay, write something up. And so we wrote a proposal up, a group of us, and we took it up to him and gave it to him. Little did we know that he sent that proposal out to NCAR staff, some NCAR staff and a university community. And I didn't find this out until many years later. The responses to that, whether NCAR, the proposal, was overwhelmingly negative. The feeling within the university community and many scientists at NCAR was that we weren't up to the job, that CGD couldn't do it. And luckily, Bob decided to neglect that opinion from the community, and he told us to go ahead. And so with the help of Bob, Rick Anthes, and most importantly, Jay Fine at the time, we were able to start coupling the model and create the simulation that Peter talked about. And I know this history because many years later, the person who had held within their hands those reviews gave them to me, and I still have them. Some of them have names on them. So I don't even know what to do with those reviews, but I still have them. So that's my funny story.
Thank you. Next, I'm going to go over to Bill, who, again, I have to appreciate because he's our current CGD advisory panel chair, but also the only person that isn't actually local, that's had to come and fly in for this session. So thank you for doing that as well.
Thank you, John. And I have vivid memories of you as a postdoc, including some rather physical interventions to make sure that I continued drinking with you. Like Jeff, I'm also struggled with how to come up with anecdotes that are suitable for an audience, most of whom I have not had the pleasure of meeting just yet. And I'm not sure if I want to start off with a particularly spicy anecdote as my means of introduction. Sort of what happened in Breckenridge stays in Breckenridge, I think is our byword here. My memories of working here were that we had a lot of very strong personalities, and that the strength of those personalities was really made the job incredibly fun. I joined in 1996. I'm pretty sure I did not have a Southern accent, but I was immediately picked on as someone who came from Tennessee. Jim Hack, whom I hope is listening, and who's now resident in Tennessee, was one of the lead teasers, and one of the great pleasures in my toward the end of my stay here was when he announced he was going to Oak Ridge. I gave him a very politically incorrect cookbook called Roadkill, for supper, and I think I doubt he still has that cookbook. Likewise, we were also, some of you may have run into Paula Fisher. She's now the head of the ASP program. Paula was, at that time, our administrator and very much responsible for keeping us in line. She was the person who, I'm very sorry to say, insisted that I take down the life-size cardboard cutout of Austin Powers from the early movies involving him as a secret agent. This was an animatronic figure, so it would talk when you walked by. And I think she got rather tired of hearing Austin Powers talk in the office. She also accused me of being a princess, so you've heard it from me. And I wear the tiara proudly, but yeah, she figured me out fairly early as someone who liked to travel a lot and had a particular lust for accumulating frequent flyer miles. The last thing so I am going just strictly with humor here, Jeff. Yeah. The last thing I'll mention, Mariana Vertenstein, who was here and was the head of the Climate, the software engineering group. I learned a lot about her life history. She's Romanian, her mother is Romanian, actually survived the Holocaust, fled Romania in the early 1960s with Mariana as a very young child, and worked in Boulder for many years as a piano teacher. Actually got written up in the New York Times. And during COVID, actually, at the tender age of 93, Mariana's mother switched to entirely online instruction using Zoom, which you just heard about, which was quite amazing for someone at that life stage. Mariana and I loved movies together, and many of you may remember there was a video store on 28th called the Video Station, closed 8 years ago. And Mariana, in one particular moment, decided to tell me that there was a movie she really wanted me to watch. And it was a Romanian black comedy called The Death of Mr. Lazarescu. And I remember renting that from the video station on physical media. And my wife and I made it about 15 minutes into the movie and then subsequently turned it off. I looked up the plot this morning on Wikipedia, of course using the internet as one now does. And just the plot came back to me. It's an evening involving an elderly gentleman who, it turns out, has intestinal cancer and is refused service by multiple hospitals. And the movie ends, and this apparently is a moment of particularly high humor, with emergency surgery involving a brain clot. And this was Mariana's attempt to draw me into Romanian humor. And I think that did not particularly succeed. For any of you who've been tracking her career, I think she's now in Norway, right, at Cicero. I look forward to meeting her again at some point soon so we can trade new movie suggestions. So with that, let me turn the floor over to Peter Gent. Peter, you're on.
Thank you, Bill.
So my story involves that every year the chief scientist has to go to NSF and give a 2-hour presentation on what the CESM project has achieved over the last year. And this is in front of the CSM Advisory Board and several program managers from NSF. We don't get reviewed before we do something, but NSF reviews everything that they give money to. So we got reviewed retrospectively from every year. And as you can imagine, this is fairly high stress for the CCSM chief scientist. One of the reasons why we've all gone this color up here. Now, one of the years when I did this, I'm not sure whether it was Jay Fine, but someone had asked me to give a part of my presentation as to if we were given sort of all the money that we could think about, how would we use that money? And so I proposed something like, several new scientists, some project scientists, some more software engineers, etc. And in the end, the total cost of that increment would be $4 million a year. So this was in the morning of the first day, and we all went to lunch. When we reassembled after lunch, Jay Fine came in and said, "Peter, you've asked for $4 million, and here it is." He gave me these 4 fake things that look like dollars that say on them, $1 million. Then he said to me, "Spend that money wisely." Jay Fine was my favorite program manager, and he did an enormous amount for this project.
Over to you, Jim.
I wish some of those old records would be destroyed somehow. So Peter, I just have to say, I'm actually jealous of your gray hair. I'm not so gray, but you've retained your hair. So that's one thing. So just stepping back very briefly, I'd just like to really thank Dave and John and Elizabeth and all the people currently involved in putting this workshop together. This is a great week, as always, and this is a really fun event and a special event, and thank you. And just Jerry, for your remembrance and of Warren. People who know me know this, but maybe some of the people that I haven't had a chance to talk to very. I'm only here, and I was only at NCAR because of Warren. Warren hired me as a postdoc in 1990, and so I had the pleasure of learning a tremendous amount of Warren's deep knowledge of the climate system for 34, 35 years that I knew Warren. But even more than that, just the incredible mentor that Warren was to so many people. I learned a lot from Warren, and it's just so nice to be able to honor his memory. In terms of my time as a CSM chief scientist, I think I struggle with funny stories, sort of like has already been said. I can think of some funny stories, not funny stories that I really want to tell today necessarily, but one of the things that came to my mind, I think I'm probably unique among all the people up here in that I am willing to bet $4 million that I am the only chief scientist who has never written a single line of code for CESM. I think that's true, yeah. For the record, for my PhD, when I was a grad student at Purdue, I worked with an atmospheric general circulation model, and I wrote some code and did some stuff for my thesis, but not with CSM. And that actually brings me to the point that I want to make in terms of my role as a CSM chief scientist. As you've already heard today, you've heard names like Byron Boville, and then the 3 gentlemen to my right. who preceded me in terms of being a chief scientist of CSM. Here I come in to this tremendously important and successful project engaging such a wide swath of the broader community, and I'm not a modeler. Okay? I'm a climate scientist. I understand atmospheric and climate dynamics and coupled variability, but I'd never actually done that, and I was fairly nervous taking on this role. It's just a matter that all of you, the entire community, everyone is so deeply dedicated to the mission of CSM. It was actually one of the best and most memorable jobs that I've ever had, having the honor of serving as chief scientist, because it's just a great community to work with, and everyone's pulling in the same direction. Everyone has the same, commitment to the mission of CSM. And so it was just a wonderful couple of years. I will say, one story that I can share that has always stuck in my mind is that while I was chief scientist, a lot of work obviously happened in developing from CCSM, the coupled, or the coupled community climate system model, into an Earth system model, CSM. A lot of that work had begun before I was actually chief scientist, but while I was chief scientist, we actually formally released version 1 of CSM. And that was a lot of fun. It was also a lot of hard work. There were some decisions to make, and et cetera, et cetera. But I remember one meeting in particular of the CSM or leadership team that I was leading that discussion that day. And at that time, Bill Large was director of CGD, and Bill came walking into the room with Francis Brotherton. And Francis has already been introduced, but if you don't know Francis, he was also a pretty strong personality. He was director of NCAR, I think, from 1973 to 1979 or 80 or so. In those days, he also served as president of UCAR at the same time. Pardon me? I think director of computing as well. Okay. But he's really, a legendary field. One of the things he's very well known for is really promoting the concept of Earth system science, the interconnected components of the Earth system, and the importance of trying to represent all of those. So here is this legendary person that comes into the room that's played all these roles at the organization, and little old me is leading this meeting about how we're going to finalize and release CSM1. And I'll just always remember that as one memory. So I think I'll just stop with that. I don't have really funny stories, but it's just a great honor to have served in this role.
Now over to Marika.
Hi, everyone. So it's such an honor to be up here with this group of people and to be at this meeting. And Dave gave us this prompt. And so I've been trying to think of something funny. And for those of you who know me well, maybe I just don't do funny. Because instead I get really emotional and I think of heartwarming things. And I don't know, that's just who I am. And it has been an incredibly important part of my career, and I am gonna get choked up because this is what I do, to be a part of this project. This project has touched so many people and so much science, and being a part of it and getting to be the chief scientist of it for several years was just an incredible honor. I don't know why this happens. I get like choked up at television commercials and stuff too. So this is just, part of what happens. Anyway, so I was trying to think of something funny. That didn't happen. Or that happened and then I realized I couldn't share those stories either. So instead I tried to think of something that happened during my term as chief scientist that I was particularly proud of. And so what came to mind is the CESM1 large ensemble, and I see Jen over there. And this effort involved a huge number of people. And the CESM project really enabled this to happen. We provided resources, computing resources, human resources, but it only happened because we're a community model. And it required the leadership of Jen Kay and Clara Desser and Paul Kushner, who was serving on the SSC at that time. And without that group of community leaders, it wouldn't have happened. And so I felt like my role in that was just to let those people do their thing and enable them and give them resources. And it had an enormous impact. I mean, for those of you newer to the field, this idea of doing a large ensemble of simulations, really being able to quantify internal variability was very new. And so it's had an enormous impact. It's led to multi-model efforts to do similar things. It's enabled a huge amount of science. And it's one of the things that happened during my term that I'm very proud of. So, yeah, thanks.
Hi, everyone. Oh, wait.
No, you can. You're welcome to go in. I've got you.
Well, that's good. You guys didn't find the 1990 picture. Deer in the headlight kind of picture. I still have it if you need it. A few things. I mean, this is an amazing group of people. Actually, Jeff is the reason why I started getting involved in CESM. I was doing atmospheric chemistry. So I'm actually probably the only chief scientist who was not a CGD member when I was selected. So I was doing atmospheric chemistry, but he decided that chemistry was actually super important, so we should have a chemistry climate working group. So that's how I got into this. But Jeff also told me that the way to have an interesting career is to switch topic every 10 years. And so I didn't quite do that, but since I left NCAR, I've been picking up the pace of switching jobs. So it's about the same. On average, I've got every 10 years now. Following a little bit. So my most memorable part of being the chief scientist. So I was in the development phase for CESM2, which was a major step in complexity in the type of processes that were being represented from CESM1, chemistry being one of them. And especially aerosols. And so one thing that we really tried hard was to really come up with a sequence of things. So this is where we are, this is where we need to be, and we're going to be so, and then we're going to leave to the very end the simplest thing, which was to change the emissions, because what could possibly go wrong? And sure enough, we did one change of one file, and all hell broke loose, and we had a cooling 20th century, which was clearly not observed. And so the thing that then, and clearly we're not as good as Peter as putting one version of the model that works right there. I was like, when does that happen? But for me, the big thing was like two things. One was this was like a few weeks before the CESM workshop, and so I was filled with like, what should I do? This looks terrible. We're not ready. What should I do? Should I say everything's fine? We're working on it. So that was, and I decided not to. And so I came to the workshop, and because I think this is important. This is what this community is built on. You have to trust what's in there. You have to understand what's good, what's not good. You have to know what is happening. And so I was really really honest about that. We got a fair amount of flack for that. There was an article, I don't remember in which, like Science or whatever, basically saying, what the heck are those people doing? Do they know anything about science? Blah, blah, blah. But I thought it was critical. I was more ready to take heat for that than to show that it wasn't working. And then again, we had to like, okay, how are we going to solve that? And we could have gone the let's increase the precip by a little factor so that it's okay, we can fix it in a day. And we could. There were very, very explicit discussion on putting a limiter somewhere. Things are going bad. Let's just put let's cut it off. Yeah, it's okay. It's just one line of code. But no, we decided, and then it was incredible because it was amazingly disappointing because we had been working probably about a year and a half putting this model together, and the last thing we were supposed to do was enough to break it. So we went back to drawing board and spent 6-8 months rebuilding. CESM still had interesting behaviors that we discovered with a little more testing, but still I feel that this was definitely the most critical event that I had during my tenure there, and so I'm glad Gökhan picked up the pieces and finished putting CESM2 together when I became CGD director. But so that's my piece.
And last but not least,
Thank you. That's probably the day I started working at NCAR.
yeah.
Yeah, that's the picture.
That's probably the picture, yeah. I mean, Peter Sok reminded me, I started working at NCAR in August of 1992. And even though I was hired to work on an upper ocean model, Saravana and I were talking about it yesterday, I ended up, my task was essentially putting GM, mesoscale mixing parameterization, and help with the KPP, that two items that Peter mentioned. So my life, since August 1992, has been all related to CESM, or CSM, or whatever the acronyms have been over the years. And I wanted to, I mean, again, we got the cues from Dave, but I couldn't think of anything really funny. And I have too many poignant anecdotes that I don't want to say here. But one thing that in early days, we didn't really have working groups at that time. And then we had, I don't know, quite a few of us meeting in director's conference room. Now it's the oceanography conference room. And we called them Principal Investigator Group. And that's called PIG. So we had PIG meetings. And when we had a smaller group of us meet, we called them the Piglet meetings. And I don't know how long that effort or the naming convention continued. Then it became the whatever the co-chairs meeting and all that stuff. But when we said, oh, I'm going to a Piglet meeting or a pig meeting. So related to my sort of time as the chief scientist, I think, I mean, one of the biggest challenges that community faced, I coincided from the dates, as you can tell, with the COVID period. And I remember our conversations with Elizabeth and many others, how the heck are we going to continue the momentum, the community momentum that we mentioned here? Because we were planning for an in-person meeting in 2020 in July, or June, sorry, and then we didn't know what to do because NCAR got shut down in March and everybody thought that it would be only for a few days, maybe a few weeks, and we know that it lasted so many years. But that has been a rather challenge, I think, for the community and for us, just to make sure that what CESM is doing continues forward. And I mean, Elizabeth spent quite a bit time, and what we tutorial, we had to switch everything to remote, and that was, I think, quite a challenge. However, just to echo what Jim said, I think it was you who said it, but it is, I mean, then you realize that how committed and how really people are come together around a particular thing. In this case, it's CESM, and you realize that not only NCAR staff members, but the community in general are really, really committed to CESM. And because of that commitment, I think, we were able to pass that COVID period, and now we are back in person, which is really great to be here. And I'm really be honored in the company of all these great people here.
Thank you for that. I was just checking how long we'd got. I didn't want to stand between food trucks and music, beer and people. But we've got a couple more questions, of which I think we could go along and just choose one of these to go along. So I wonder whether you might choose actually from questions 2 and 3 and choose which one you want to answer. So there's opportunity to share your thoughts on the future of CSM or system modelling as a whole, or what you think's been one of the most impactful CSM activities, which we're particularly interested in right now because this US government's got some funny ideas. So let me go start. We'll go in the same order again, I think. So I'll go to Jeff first, and yeah, just choose one of those two.
I'm going to answer both of them. Very quickly, the future of CSM. We're in a very difficult time right now in this country with regard to science. And I think it's extremely important that each of us take any opportunity we can to learn to communicate what you do as individuals, as scientists, in language that is understandable to as many people as possible. You know, Richard Feynman once said, if you can't explain the science that you're doing simply, you don't understand it. And I think that's true. And so each of us as scientists has a responsibility more than ever right now to communicate to as many people as possible, your neighbors, your community, the science that's being done with CESM in a language that's accessible to the person you're speaking to. And as many of you know, this was a big thing with me just before I left NCAR. I was talking a lot about how to better communicate the science that we do. And unfortunately, scientists still are struggling to learn how to communicate their science in a way that most people understand. So I think that's number one. Given the situation that we're facing as a nation right now. The second issue, what was the second issue?
Impactful, or
the impact.
Kind of combined, I think.
Well,
in your answer.
I'm going to say, you know, for me, it's the openness of this whole process. From day one, it was decided that our code would be open to the community, that we wanted the community to be involved. This was not an NCAR-centric activity. It began that way because it had to, but it very quickly, through the working group structure, the purpose of the working group structure was to entrain as many of the university community as possible to be participants, not just in using the model, but in contributing to the development of the model. I think you have to realize that at that time, and I still think it's unique, but at that time, no other modeling center was doing that. No other modeling center allowed anybody to look at their code. No other modeling center was giving their code to anybody that wanted it. And the communities that were working on developing those models was very closed. And what made CSM and CESM unique, and still tremendously unique, is its openness. And I think that is truly something that needs to be continually touted to the world, that we truly are a community Earth system modeling activity.
Thank you.
Yeah, likewise, I'm going to answer both questions simultaneously. CESM has built a really phenomenal cadre of early career scientists through its history. The fact that it's been made openly available to graduate students and postdocs has allowed many, many scientists to cut their teeth on a bleeding edge tool and to learn how to do climate science. And I can speak from personal experience of being mentored by Jeff. The CESM also holds itself to a very high standard. So it's not just getting a plausible answer for what might be the right reason. The standard is getting the right answer for the right reason. And that it's very much baked into the way that CESM works. It's baked into the way that the model has been shared with the community. And I can see it as a member of the CGD advisory board, how much effort goes into continually refining the model to make sure that it is accessible to even more people and even more broadly used worldwide, several thousand installations worldwide at current count. If you were to ask me what its legacy will be 30 years from now, I think it's going to be the fact that all those early career scientists whom you've trained, either directly or indirectly through your mentorship programs, through your training directly or by just sharing the model with them, those scientists are going to go on to train their own students and their own postdocs. So this is, the CSM is like a wave that's propagating and having a bigger, the ring of impact is just continually growing with time. It's remarkable how successful it's been. So I would really applaud the institution for having thought up the idea of being brutally open and living in a glass house. That model has proven to be remarkably successful. And just think about all the people who've launched their scientific careers and gone on to do great science with CESM. And I think it's evident that the model has proven itself to be literally unique worldwide in its success as a climate model. So thank you.
I want to just point out in an early meeting when we were designing this, Suki Manabe was there, and he said, beware of building a glass house. People will feel compelled to throw rocks at it.
So, starting at the meeting last year, I was really impressed with the results that have been got from the high-resolution version, the one that used a 1/4 of a degree atmosphere and a 1/10 of a degree ocean. There's a 10-member ensemble of that, and one of them really produces the change in the surface temperatures from around the globe that quite closely resembles what actually happened over the last 25 to 30 years. I was really impressed with that, and more recently, I've been working with John Fasulo, who shows me that the sea level rise that's produced in that version most closely agrees with observations of sea level rise that have been made over the last 30 years. So I was really impressed with that one run. It's interesting that it doesn't look very much like the ensemble mean, but it does look like what the Earth has done. And when you run a 1/10 degree ocean, you don't need that lousy parameterization of what those mesoscale eddies do. Answer the third question, I think the education part has been really unique. For many years now, I've given a talk at the tutorial, and I think that introducing those tutorials has been extremely good to educate the upcoming people in how to use and run a climate model. So.
Feel sorry for everybody to the left because I don't know what you're going to say by the time we get down there, because but you'll come up with something. I have confidence. Yeah, I'm going to just reemphasize a couple of things and then maybe one or two additional thoughts. In terms of impact, I mean, for me, it is the C, right, in CESM, the community aspect of this, the openness, the transparency that Jeff spoke to. I think it's just hard to overemphasize how critical that has been. And I think it's just, you know, it's a model and it's not perfect. But when I think about the community that is engaged, spanning these disciplines, I mean, we talk about interdisciplinary science and just thinking about the range of people here in this room. You look at the working groups, all the different working groups, the communities that convene under the names of those working groups and then all come together. It's really just staggering, the science that has been enabled by all of the work that has gone into CSM. And it's been successful because of the C, because of the community aspect. So I just want to second that. You know, I spent most of my career at NCAR, but I've spent the last 6 or 7 years at Colorado State University in a atmospheric science department, and I have graduate students now, and I have postdocs. And one of the things that I do want to take a moment to mention in terms of impact, yes, the training, Cecile, thank you for the tutorials and all of the staff that are involved in putting those tutorials together. It's not trivial by any means. That's important, learning to run the model and whatnot. But the data sets, the community data sets, right? I mean, my students have just feasted off of the large ensemble data sets, off of the Mesa Clip project, the relatively high resolution runs, which I think I agree with what Peter Gent just said. Really fascinating, interesting runs to look at. You know, the experience in analyzing climate model data and comparing to observations and whatnot that's enabled by the effort that goes into producing community data sets and then analysis tools, right? And all of that. I don't want that to get lost. It's more than just whatever, 4.5 million lines of code, right? All of that effort has been remarkable. In terms of future directions, God, that's a tough one, right? Because of everything that I just said, the importance of all the different CSM activities and supporting the broad community, you don't want to lose any of that. And that's always been a challenge, right, with CSM. There's just more and more and more, and you don't want to take anything away. I think CSM, as Everett Joseph said yesterday, it is a facility. It is a community facility. And how to keep that community facility, like Jeff says, talk about it, et cetera, et cetera. But when I think about new directions, I guess I just want to say that, you know, I'm excited by tomorrow's cross-working group sessions on how CSM can leverage machine learning. Machine learning is revolutionizing in AI, you know, many aspects of our field. And so CSM not being behind the curve on that, but engaging with that and thinking of the advantages that can bring is really important. And then as Peter was just saying, you know, high resolution in the context of like Ping Cheng's talk yesterday, 10 to 25 kilometer kind of resolution is really amazing. Some of the improvements, I get it. Resolution is not a magic bullet. It's not everything. There's all this other science that needs to be done, paleoclimate applications and whatnot, but I think the high resolution aspect is really, really interesting. And then the ultra high resolution, right? Thinking about kilometer scale modeling. And there's been projects like Dave Randall talked about yesterday, Earthworks, Storm Speed, these growing efforts in developing kilometer scale resolution. And I think that that's a really promising direction, not only because of the benefits in simulated climate, but different ways the modeling system, even more communities, the modeling system can entrain as we move into the future with that kind of ultra-high resolution capability where you can do weather forecasting and prediction, tropical cyclone studies, I mean, all these kind of things that you can do now, but perhaps arguably even on a firmer scientific ground moving forward by ultra-high resolution. And I think about the talks by Hansi and Paula yesterday, engaging with communities like insurance and reinsurance companies and water managers and city planners, and the kind of opportunities maybe that ultra-high resolution might bring to CSM moving forward. And dare I say it, but even the current administration, right, with their focus on economic prosperity and national security applications. And I think there's interesting things to think of how those higher resolution versions of CSM can be brought to bear on sort of shorter time scale predictions, the Earth, what is it, Yaga? Earth prediction across timescales, Earth system prediction across timescales initiative, in the central role that a higher resolution version of the model might play. So I think that's a really exciting future direction.
Thanks.
So Jim kind of stole my thunder a little bit. As you said, it's going to get harder as it moves down the table. I just want to echo what other people have said, in that I think the community is what makes CESM special. And I think the fact that we have such an engaged community is amazing, and it improves all of our science, and it helps us build better tools and all of those things. I think the science is heading towards there being new communities to engage with, much like Jim just said. That includes practitioners, that includes machine learning experts, data scientists, et cetera. I think we're doing a really good job in training some of those communities. I think the work that's being done with machine learning and building parameterizations that are machine learning based, or emulators, things like that, we're definitely doing that work, and that community is, I think, being incorporated very seamlessly within the CESM umbrella and framework. Other communities are harder, I think, practitioners, local communities. I think there's efforts underway there. We saw great talks yesterday from people that are more in the practitioner space. I think we need to be really thoughtful about how we also incorporate those communities within the CESM umbrella, and learn from them in terms of what information they need in light of the extreme changes happening in the climate and how we're going to deal with those. And that's a really hard problem, because all of those problems are local problems, right? Or a lot of them are local problems. We can improve resolution and provide more useful information at those scales, but how to scale that up, every community is unique. Every location is unique. And so I think it's a challenge for us. So thankfully, Dave's in charge, and I'm sure has brilliant thoughts about how to do this.
No pressure.
But, I think it's something that we should be really thoughtful about how we do that work, and how we do it in a way that is possible, but also involves the right communities and, learns from the people that are being impacted by the kinds of changes we're seeing in the climate. So it's, maybe it's a challenge for us, but I also think it's critically important. So yeah, I'll just end with that.
Thank you.
All right, so indeed, being at almost the end of the line makes it a little harder. But one thing that has not been mentioned, I think, is one of the strengths of CESM is its portability. I mean, the fact that you can run CESM on so many platforms almost without trouble is an achievement that very, very, very few, if any groups out there has actually tried. And it's a problem. I mean, it makes it really hard. It's limiting. You can only do, you can only write the code so well. It has to be working on so many platforms. But then it really enables people who want to do science, who don't have access to blah, 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 supercomputer, they can actually do science. They can actually use that. And I think that's a strength. And this is all due to the work that Mariana and all the software engineers of CESM are enabling. And I think it's a really immense bonus to the research community to have that. On the impact, one thing that since I left NCAR, I've been on the private sector side of things and seeing from a little bit closer some of the work that is being done, good and bad, on climate impact and how climate impact are being taken into consideration for decision making. And my very limited view of that is that it is critical for a group like CESM and all the scientists involved to develop the best models they can. Because in the whole process that Marika has described of generation of information, the place where fundamental science will be put is here. And if it's not done here, it's not done. Downstream, people are going to do as quickly, as cheaply as possible to get the answers that they need. And so the responsibility of this group is to make sure that whatever data are being generated, large ensemble, everything, CMIP, which I was amazed when I went to McKinsey. People were like, CMIP 6, CMIP 6, CMIP 6, CMIP 6. Everyone knew about CMIP 6. Everyone used CMIP 6. If there is no CMIP, there is no information about future climate conditions. That's just the bottom line. So I think it's really critical to have the science. Going into the future, I think it's the connection, and I see Hansi there, and she remember some of the discussion she had a few years back again when I was at McKinsey, and I think there was some of the most brilliant views on how to actually combine what CESM can offer, something like decadal prediction, which I think is an amazing capability, with a twist. How do you go further? How do you go to the next level? How do you build what actually is realistic, usable information that people will want? And so I think this is really trying to find and build those partnerships with people outside that can really take CESM and the impact of CESM to the next level, is to make sure that we can't do everything. But what we do, we have to do it very well, because afterwards people are going to be relying on that. So, thank you.
I'll cut it short since I was going over my list. There's nothing left here for me to say. But, I just wanted to stress the community aspect as everybody else. And over the last several months, I'm more and more realizing that it's always good to go after the next shiny thing. But however, under the circumstances, I think we need to be mindful of protecting foundational and basic science. Because if we cannot protect that, the next shiny thing will not be there. So I think we need to be really sporting basic science, basic Earth system modeling science, and foundational science. And while also pursuing high, ultra-high, AI/ML, GPUification, and all those efforts at the same time, while at the same time, with perhaps reduced resources, supporting the community needs all the way from coarse resolution to ultra-high resolution. And that requires essentially a hierarchical modeling approach that each group or each section can learn from each other. Thank you.
Thank you. I guess it's just for I guess it's just for me to try and reflect on that to wrap up before we go and have some fun. So I've been in CGD just under a couple of years now, apart from the time I was in before. And the most striking thing I've come across, and you know, people ask about what's it like in the job and things like that. It's the passion of the people, the passion of the staff in CGD, that's the software engineers, the scientists and the administrative staff, about delivering quality models, science, and as has been touched by all the chief scientists, engaging with the community. And then, having been in CGD and engaged with the community, I've recognised the passion of the community and I'm wondering whether we rebrand actually, so it's PCESM. It's the passionate community system model. Maybe that will bring in some funding as well from some sponsors. But yeah, that's what's really struck me. But it's there in all the chief scientists. You know, that passion hasn't gone away. People have come through and led this, and they're still passionate about it now, and that's what's so amazing, and I really appreciate all their comments and everything. So one massive big thanks, and let's include Dave in this as well now. Some big massive thanks for the chief scientists and their passion.
Okay, so let's go celebrate. We got food and alcohol and other drinks, and we have a food truck out there. We definitely need people to go to the food truck, otherwise we're gonna like get in big trouble with the food truck company. they're gonna kneecap me or something like that probably if we don't buy enough meals. So I really need you to go out there and get that. Let's have fun. Thanks again to all you guys for coming here. It was really, really fun and really appreciate it. So see everyone. Thanks a lot.